Have you ever wondered why the sky above us is so dependable? Our sun isn't prone to violent tantrums. It doesn't blast us with deadly radiation on a whim. Instead, it maintains a steady, quiet presence, like a campfire that never rages and never sputters out. This profound calmness is not a given. It is a quiet miracle in a violent cosmos, a background hum of stability that allowed oceans to pool, atmospheres to settle, and life to begin its 4 billion-year journey from a single cell to a thinking mind. That steady light is the secret ingredient. To understand our good fortune, first picture a different kind of fire, a match. It flares into being with an intense, brilliant burst of light, and then, in a breath, it's gone. Many of the most massive stars in the universe are like this. They live fast and die young, pouring out staggering amounts of energy in a cosmic sprint. A planet orbiting such a star would be scorched by its intensity, never having the time to cool, to form stable oceans before its sun burned out and vanished. Now, picture a candle in a draft. It flickers and sputters, its light jumping and dancing unpredictably. The most common stars in our galaxy, the small red dwarfs, can be like this. They spit and dim and erupt in violent flares without warning. If you were a tiny world huddled close for warmth, you would be hot, then cold, then blasted with radiation. It is hard to build a lasting home when the only light you have is a chaotic, angry flicker. Finally, return to the bonfire. Not flashy, not temperamental, just a deep, abiding warmth you can count on. Our sun is that fire. For billions of years, it has burned with an almost unbelievable consistency. The day-to-day weather on Earth may change, but the energy arriving from our star barely wobbles. This profound patience is the greatest gift our sun has given us. It bought Earth the one resource that complex life needs above all else: deep, uninterrupted time. Our sun is what astronomers call a G-type main sequence star, a sort of stellar middle class. It's not among the biggest and brightest, nor the smallest and dimmest. It has been steadily burning for about 4.5 billion years, and it has about 5 billion more to go before its stable life ends. That 10 billion-year fuse is incredibly long, and stars like ours are surprisingly uncommon. They make up less than 1/10 of the Milky Way's stellar population. We live in a quiet suburb of a galaxy dominated by cosmic cities and volatile frontiers. Just how stable is it? Over its 11-year cycle of activity, the sun's total brightness shifts by only about 1/10 of 1%. Think about that. The total energy output of a nuclear furnace, 1,000,000 times the volume of Earth, barely budges. On our world, a single passing cloud can block far more sunlight than the sun's own internal rhythm. These cycles bring more sunspots and more beautiful auroras at their peak, but they are just gentle ripples on the surface of a vast, calm ocean of energy. The oceans don't boil, and the ice caps don't melt just because the sun is having a busy year. Earth's own motion adds to this stability. Our planet's path around the sun is very nearly a perfect circle, meaning we don't swing dramatically closer and then farther away. The distance is constant. This is why our seasons come from our planet's gentle tilt, not from a chaotic orbit. Summer and winter arrive because one hemisphere is leaning toward the sun, not because the star itself has changed or because our distance has wildly shifted. Our seasons are a predictable dance of geometry, not the result of a star's temper tantrum. Life can build its rhythms around that. Over deep time, the sun does change. It gets about 10% brighter every billion years. But that pace is glacially slow, and it has allowed Earth to have a conversation with its star. Our planet has a kind of geological thermostat. When the sun gets a little brighter and the planet warms, more water evaporates, creating more rain. That rain washes carbon dioxide from the air into the oceans, where it gets locked away in rocks. This thins the greenhouse blanket and cools things down. This slow, planetary-scale feedback has kept Earth's climate in a habitable range for eons, all because the sun's changes were slow enough for the Earth to answer back. Now let's pull back again to the galactic family of stars. The giants, the brilliant blue and white stars, burn like cosmic torches, hundreds or thousands of times brighter than our sun. But they pay for this brilliance with their lives. They burn through their nuclear fuel in just a few million years, or perhaps a billion for the more modest ones. Before a planet around them could even fully form a crust in oceans, before life could get beyond the simplest microbes, its star would die in a violent supernova explosion. There is no time for a long story. At the other extreme are the little red dwarfs. Cool, dim, and incredibly long-lived, they can sip their fuel for trillions of years. But they present their own challenges. To stay warm, a planet must orbit incredibly close, so close that the star's gravity likely locks it in place, with one side in perpetual baking daylight and the other in unending frozen night. And these stars are notorious for their violent flares, which can erupt with enough high-energy radiation to strip an atmosphere away and sterilize a world's surface. It's a life of eternal twilight or searing day, punctuated by cosmic violence. We don't have to look far to see this. Our closest stellar neighbor, Proxima Centauri, is a red dwarf. It regularly unleashes flares that can spike its ultraviolet radiation by a factor of hundreds or thousands for minutes at a time, a devastating bath for any aspiring life on its nearby planet. The famous TRAPPIST-1 system has 7 Earth-sized worlds, all huddled so close to their tiny star they would fit comfortably inside Mercury's orbit. This star also flares often. They live in a very different and very dangerous neighborhood than our own. If you find a sense of peace in these quiet journeys through the cosmos, you can subscribe to the channel and come along for the next one. Our sun wasn't always this calm. Like most young stars, it was born spinning much faster, a wild and tempestuous youth. A faster spin drives stronger magnetic activity, meaning the young sun threw far more tantrums, more flares, more violent outbursts. But over billions of years, the sun tamed itself. The solar wind, the stream of particles flowing from its surface, acted like a brake. By flinging mass out into space, the sun slowly bled away its angular momentum, and its rotation slowed to the stately 25-day pace we see today. As the spin slowed, the magnetic engine grew quieter. In its youth, its X-ray output was likely 10,000 times stronger than it is today, a constant roar that has since faded to a whisper. This stability doesn't mean the sun is a frozen statue. There are still variations. Between the years 1645 and 1715, sunspots almost completely vanished from its surface. During this period, called the Maunder Minimum, parts of the northern hemisphere experienced a spell of colder weather, part of the Little Ice Age. The sun's lull likely played a role, though volcanoes and ocean currents were also factors. It's a reminder that our star breathes, but its breaths are now long, slow, and gentle on human timescales. The sun's slow brightening over deep time is the key to one of Earth's great survival stories. 4 billion years ago, the sun shone with only about 70% of its current brightness. By all rights, the infant Earth should have been a frozen ball of ice. Yet we have clear geological evidence of liquid water oceans. This is the faint, young sun paradox. The solution, it seems, was that early Earth was wrapped in a much thicker blanket of greenhouse gases, trapping what little heat there was. As the sun slowly, patiently grew brighter, Earth's geological thermostat slowly, patiently removed those gases, keeping the climate in balance. This incredible grace period allowed life to climb a 4 billion-year ladder. For 2 billion years, life was just simple cells. Then, around 2.4 billion years ago, came the Great Oxidation Event. It took another 2 billion years for the first complex animals to appear in the Cambrian explosion. Each step was a planetary transformation that required immense, unimaginable stretches of quiet time. Time for mountains to rise and fall, time for continents to drift, time for evolution's slow, meandering search. All of this was possible only under a star that held steady. But this grace period is finite. The conversation between our planet and its star will eventually end. As the sun continues its slow, inexorable brightening, in about 1 billion years, Earth's thermostat will be overwhelmed. The planet will tip into a moist greenhouse state. The oceans will begin to boil away into the atmosphere, which will then be stripped away by the solar wind. Earth will become a dry, dead husk, long before the sun itself begins its final transformation. In about 5 billion years, it will swell into a red giant, finally engulfing whatever remains of our world. Stability is not a promise. It is a window of opportunity. For now, and for a long time to come, we live inside that window, the quiet, gentle middle of our star's long life. Here is the thought that truly stops me. On a planet that had time, under a star that could wait, matter woke up. Our consciousness, our questions about the universe, our art and our science, all of it is what hydrogen, burning calmly for billions of years, can eventually do. The universe is full of stars, burning with every kind of fire imaginable. But patience, the kind of patience that allows a world to think, may be the rarest light of all. If this kind of quiet cosmic wonder speaks to you, subscribe and drop a like. There are more journeys waiting for us, from black holes to the fate of the last star. Take care and see you next time.